Your phone. Yes. We're going all problems this time. So good morning. So today is October 25, October 25th. And as discussed previously, today we're going to have our review for the second exam, which is scheduled for Wednesday this week, October 27th. And as you're noticing now, the slides are going to be opening right now, so you should be able to access them in the modules. But what you're going to see is what we're going to discuss right now. So the second exam, this exam will have no true or false or multiple choice questions. It's going to be all problems. The reason is this particular exam has a programming component, so I decided to put more emphasis on that programming part and not necessarily on those true or false questions. So the first part is going to be, you're going to have 90 minutes. I'm pretty sure that you're going to be able to finish that first part before that time period. So it's going to be 3 problems to be solved by hand. And these are short answer, explanation, or mathematical. And the exam, both parts are going to be online. Okay, so you'll be working online. You're going to be working by yourself. In Canvas, you will get access to the exam, and you're going to upload everything in Canvas. So for the first part, you have 3 problems. And if you think about what we have covered for this second portion of the semester, you should expect a problem in which you're going to solve using the Simplex method with less than or equal constraints. And then you should expect a problem in which you're going to implement the M method, and also a problem in which you're going to implement the two-phase method. For the big M method and the two-phase method, I might ask you to complete only a portion of the problem, not the complete full iterations. So I'm interested. For the first one, I can ask you to do the whole thing, to solve the problem using the Simplex method. But for the big M and the two-phase method, I'm more interested in seeing whether or not you understand how to find a starting feasible solution using those 2 methods. After you show me that you can do that, then the rest is just applying the Simplex method. So for the first part of the exam, you will have 90 minutes. So the exam will be available on Wednesday, and October 27 at 9, which is I'm sorry, it should be 9:30. Apologize for that. 9:30, which is the scheduled class time. So I'll fix that in your slides. So the exam will be available at 9:30 a.m., which is the scheduled time for this class. And then you will have until 11 to submit your exam. So my advice, and I'm going to go back to this towards the third slide. My advice that you stop working at 10:50 and then make sure that you have enough time to upload your materials. Okay, so the exam is going to close at 11, 1 hour and 30 minutes or 90 minutes to complete this first part of the exam. So again, it should be more than enough time. So make sure that you plan accordingly. and that you upload your materials on time. And then we have the second part of the exam in which we're gonna have two problems to be solved using the computer. For this part, you're gonna have 24 hours. So this one again, I don't know what I was thinking. It's gonna be open at 9:30 a.m., which is the scheduled time. And then for this second part, you're gonna have 24 hours. So you have two problems to be solved using the computer. So one of the problems I'm gonna ask you to solve it using Excel. The second problem you will be asked to solve using Ample. So you have 24 hours to implement this. I can ask you to formulate and solve the problem. So I advise you to review those problems in lecture 3 because most likely the formulation will be close to one of those problems shown in that lecture. So lecture 3, problem formulation. So you go through the entire process of reading the problem, formulating the problem, and then solving it using Excel and Ample. Yes. Yes, that's correct. So for the Ample, I show you how to solve a problem in Ample just by creating a mod file, a .mod file. And I also show you how to solve a problem using an MOD file and a data file. So if you just go and implement the mod file, the MOD file, and solve it using the MOD file, that should be fine. Okay, you will get the full credit. But if you want to go and do both, then it depends on how you want to approach it. But yeah, if you just submit the mod file, that should be fine. So let me go back to this. The exam will have two parts. Exam part one will have 3 problems that for you to solve by hand. This will be online. The exam will be online. You'll be having access to this exam on October 27, which is Wednesday at 9:30 a.m. And you will have 90 minutes to complete this part. So 3 problems, Simplex method, Big M method, and the two-phase method. So you should have enough time to work on those problems and upload. So these 90 minutes should be more than enough. And then the second part of the exam is when you're gonna work with the computer, implementing the solution or solving these problems using Excel and using Ample. So one problem with Excel, one problem solving using Ample. The exam also will be online. And for this second part, you will have 24 hours. So the exam will also be available on Wednesday at 9:30, and it's gonna be due the next day at 9:30 a.m. So 24 hours should be more than enough. I'm giving you this time period just because I know you have other classes and you might be busy during the day, but I think you should be able to do this in less than 1 hour and a half or 2 hours max. So any questions about the format? Yes. No, no true or false questions, just problems and computer implementation. Yeah. Any other question? Good. So again, you don't have to come to class. If you want to come to the classroom and work on the exam here using your computer, that will be fine. I'll be here on campus. I'll come to the classroom in case you need access to the computer. So I can provide you with access to the computer, but you don't have to be in the classroom to work on the exam. I'll be here just in case you don't have a laptop or you don't have access to the software. I can share with you one of the laptop computers and you can work from here, from the classroom. But if you have access to the software and you can work from home, that's fine. Yes.
My question was for the first part.
Yes, yes, you can just solve it in a piece of paper and take a picture and upload the solution. Yes. Or scan the document if you have a scanner. Yeah.
For the first part, you said
The big M method. Okay, so I want to make that very clear. So if you don't have a computer, okay, if you don't have a computer, and if you don't have access to Ample in your computer, I'll be here 9:30 a.m. on Wednesday, so I can provide you with a laptop, provide you with access to a computer. Okay, so I don't want that to be an obstacle for working on this exam. So if you want to contact me today or tomorrow to plan for a time period to use a computer, let me know. But if you have access in your machines, then you can work from home. Any other question? Nope. Okay, so yes.
So you said for one part we have to go back to lecture 3.
For this second part, what I'm saying is that I can ask you to formulate. Let's say I can tell you this is the problem that you have to solve in Excel, and this is a single period production problem. So I'm expecting you to know how the formulation for a single period production problem looks like, because we did that in class. So what I'm saying is go back, review those slides, because if I give you the problem description, and I tell you this is a single period production problem, I'm expecting you to know what I mean by that. So you can go check the formulation and then formulate the problem using that guideline. Okay. If I tell you this is a scheduling problem, then we discuss also scheduling problems. So I'm expecting you to use the data that I'm giving you to formulate the problem using that formulation. Okay. Good. Any other question? So my advice would be go review those slides so you know what to do once you see that problem. You know, okay, single period production problem. Just have to. This is the template. This is what I'm gonna do to formulate the problem. This is my data, and then I solve it using the computer. So in terms of the lectures to study, we started this second part of the semester with lecture 4, the simplex algorithm. So make sure that you understand how to solve problems for minimization and maximization using the simplex algorithm. So converting an LP to standard form, transition from graphical to algebraic solution, a preview of the simplex algorithm, and then the simplex algorithm. So we discussed a problem in class, and then we spent one of the lectures just going through one problem step by step. If you don't remember, you can check the videos, but we spent one day just going through one problem. And then we did the assignments, so the solutions are available. So we have plenty of practice. So make sure that you go understand what we did in class and in terms of applying the simplex algorithm. That'll be the most important skill that I want to test in this exam. So you understand how to apply the simplex to solve a linear programming model. And then the next slide, we have solving LP problems using the computer. So again, we spent some time going over both of them, solving problems using Microsoft Excel. So you use the solver add-in, you set up your problem in Excel, and then you set up your decision variables, you set up your objective function, and you set up your constraints. You use the solver add-in to set up the cells corresponding to each one of those, that information corresponding to that information, and then solve using the Excel file. I'm sorry, the solver in Excel. So what I'm expecting you to upload will be the Excel file, basically with the code. So that's all you will be submitting in terms of solving the problem. Then for solving LP problems using AMPL, you'll do the same thing. You will set up your formulation, and then you will implement that formulation in an .mod file. So you will state the parameters, decision variables, the objective function, the constraints. And obviously, I'm going to be running the file just to make sure that it's working. So make sure that you have an executable file that have no errors. I encourage you, always not encourage you, but I ask you to make sure that you work on this independently. It's pretty easy for me to find out if the code is being shared. So just make sure that this is your work. And then lecture 6 is the artificial starting solution. So we work with the two methods for solving problems that have constraints that are equalities and greater or equal to, or a combination of those. So how to set up your problem, and also how to find a initial feasible solution for your problem using the M method and also the two-phase method. So those are the 3 lectures that we cover after the first exam. Yes. Yes. So the exam will have a problem on the simplex method, in which you're going to be solving the problem using the simplex, and then another problem in which you implement the M method, and another problem in which you implement the two-phase method. And that will be the first part, or exam part 1, and then the second part will be the coding. Yes. Yeah. I will. At least I will ask you for, you don't have to tell me this is the numbers, the solutions. I would get that solution from the file, but I think I will ask you for the formulation. If I ask you to formulate the problem and then implement it, in case the formulation is incorrect, I don't want to penalize your code. So I will ask you to submit the file with the formulation, so I see the file corresponds to the code that you implemented. So you will have to show me the problem formulation in a piece of paper, and then also upload the file with the code. And now that I'm thinking about it, I need to see the formulation. Yeah. Yes. So the formulation has to be there. The piece, the problem formulation, so I can connect the formulation with your code. Okay. So yeah, that's a good point. Any other question in terms of the exam? And I have more information here, how to prepare for the exam. So good thing about this transition that we did after COVID is that you have access to the videos now. So if you want to go back and check those videos in terms of preparing for the exam, those are available. Also, the lecture slides with the notes and the labs and the assignments with the solutions should be all posted by now. So the instructions for the exam is closed book and notes. The link to access the exams, part 1 and part 2, will be available in Canvas in the modules. Clearly show your work and formulas used in your solutions. This will help me award full and partial credit. So exam part 1, This will be questions, problems. You're gonna have to upload the file for each one of the problems that you are working on. So work your solution in a paper, take a picture or scan and upload your solution file. You will have 10 minutes to upload your file. Basically, what I'm saying is you start at 9:30, which is the scheduled time for the class, and you work until the end of the time period, it's 10:50. So I'll give you those 10 extra minutes for you to upload the files. So my advice is for you to start working in the exam at 10:50 a.m. and use that time after to upload the files. The exam will close at 11 a.m. The first part. Second part, questions, problems, you're gonna upload the files as I just mentioned. You for both of them, you're gonna have to show me the formulation and you're gonna upload the Excel file for the first one and the ample upload the .mod file. At the minimum, the MOD file, if you decide to go for adding the data file and the ROM file, that's up to you. But at the minimum, I want to see the .mod file, which is the model file. Okay, so exam one, you have the scheduled time period for the class to work on the first part, and then for exam part two, you have 24 hours. Just want to make that very clear. So you work on your code, and you don't have that time pressure. Make sure that you code everything right, and then you upload by the next day at 9:30. Yes. Oh, not needed. Run file, I guess I always show you how to run the file using the .run file, but you can actually type those instructions in the console. Those instructions that are in the run file, you can type them in the console, and it will solve the problem. So this is basically the run file is saving you time instead of just typing include the mode files, include the Simplex, and then solve. You can type that in the console, and it will solve it for you. Yeah. So at least we should have if you just provide me with the mod file, I should be able to run it without a problem.
So, like for this thing, it has like problem 1, 2, 3, and let's say we have picture total 6 or 5. Am I gonna upload like the whole PDF file, or you want like one file?
That's a good question. So thank you for that question. So I will give you, let's say we had 3 problems for the first part, and I will give you a space for you to upload each problem, like the file for each problem. But if you want to group all the files into a single file and upload that file into one of those questions, that'll be fine too. So you don't have to split the PDF files and then upload independently. So whatever works for you. If you just want to group all the PDF files for all questions into a single file and then upload that into one of those questions, I will accept that. Yeah, good question. I always forget about that, but yes, you can do that. Any other question? So I'll be sending an email today just to remind everybody about the exam on Wednesday. I want to make sure that everybody's aware of the instructions. I will put this file also as an attachment, so you get a reminder for the exam on Wednesday. And again, if you don't have a computer, you don't have access to the software, Ample, or the solver in Excel, I'll be here on Wednesday at 9:30 if you want to come, and I will facilitate you with a computer. So I just wanted everybody to be aware of that. If you have access to a computer with internet and the software that you need, you don't have to come to the classroom. Okay, so these are the problems that were assigned in this assignment. Assignment 5 was due today. So I just want to go over those, check if you have any questions. So this is the first problem. Consider the following set of constraints. And then there were two parts in this problem. The first part was to solve the problem using an objective function in which you're maximizing 2x1 plus 3x2 minus 5x3. So you'll be using the same set of constraints for part A and part B. So we're going to start with the maximization. So as you can see now, you have two constraints in this problem. One of them is inequality. The second one is a greater or equal to constraint. So for us to be able to find an initial solution for this problem, we know that we're going to have to use artificial variables for both of these constraints. Also, for the second constraint, we have to include an excess variable, or we have to subtract an excess variable in order to make that constraint an inequality. So once we make that constraint an equality, we can add also the artificial variable corresponding to that constraint. So the way I went to solve this problem was to use the big M method. So you can see for the first tableau, we have a maximization objective function. Yes, sir. No, that's not true. So basically both methods are designed to solve problems in which you have to rely on the artificial variable to solve the problem. So you can use either one for maximization, you can use either one for minimization. So I made a decision to use the M method in this problem. But you no, well, I think from my perspective, this one is easier to implement. But yeah, I think that's where I went for this one. Yeah. So again, you can use the big M method for maximization and minimization. You can use the two-phase method for maximization or minimization. So in this case, I'm using the M method. I'm relying on the artificial variables to find an initial solution. So I'm using M equals to 100. So you can see that in row 0 for the first table. And then the first step will be to set up this, make sure that this solution is consistent. Yes, just one second. Make sure that I set up this. Yes, what's your question? So we formulate this problem. Is going to be the maximization. So Z equals 2x1 plus 3x2 minus 5x3. So since we are maximizing, we are subtracting 100 times R1 minus 100 times R2. Yes, so if you're maximizing, you want to penalize the objective function, right? So the way to penalize the objective function is to subtract the artificial variables. Because if you increase the artificial variable, your objective function is going to decrease. If you're minimizing, the way to penalize the objective function is by making those artificial variables positive, because if you increase the artificial variables, your objective function is also going to increase. So you want to go the opposite way. That makes sense? Yeah. 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 Okay. So yes. And then the subject to x1 plus x2 plus x3 equals 7 to x1 minus 5x2 plus x3 e1 plus so as we have discussed, for us to set up the objective function, we have to make sure that we move everything to the left side. So we have z minus 2x1 minus 3x2 plus 5x3 plus 100 r1 plus 100 r2 equals 0. Yes.
These may be different colors show us if you have constraint that is less or equal.
Oh, so if it is the question is what will happen if we have a less than or equal to constraint, right? That's the question. Yeah, so if you have a constraint like this, let's say x1, and this is again not part of the problem, I'm just adding this for the to answer your question. For x3 less than or equal to 5, we have something like that, then we formulate that constraint. We want this to be an equality. So the way you make that inequality is by adding a slack variable. No, no. No artificial variable will be needed because that slack can help you find an initial solution. So slacks are good in terms of helping you find an initial solution. So if you have a slack, then you don't have to worry about adding an artificial variable. Problem is when you don't have that slack. So you have to use the artificial variables. So let me remove that so you don't get confused. So that's why when we solve the problems at the beginning, using the simplex method at the beginning, if you go to lecture 4, you'll see that we started the discussion only with constraints that were less than or equal to, because if that's the case, you don't need the artificial variables. You always find an initial solution using the slacks. Right, so if you go back to lecture 4, you will see that we solve only problems with less than or equal to constraints, and we didn't need the artificial variables for those. The artificial variables show it up after we started looking at problems with greater or equal to constraints and equality. Yes. Subtract R1 and R2, no. They're going to be added to the constraints. So so what we have in this first tableau is basically row 0 is this part, this setup, and then we have the coefficients for these two in rows 1 and 2. So at this point, always remember that we need to, before we start solving the problem, we need to make sure that this tableau is consistent with the solution. Okay, so if you go try to solve this using the simplex method, you will get it wrong, because you always have to look at the identity matrix, make sure that those columns are consistent. So you have a coefficient of 100 for both of them, so you have to make those 0 before you attempt to solve this problem. So that's what we are doing in this part. We made this 0, and in this part we made this 0. At this point, we can start solving the problem using the simplex method. Does that make sense? Right? So now, after making sure that this is consistent, now we can implement the simplex. Since this is a maximization problem, we're going to look for the largest negative coefficient, which belongs to x1. That's negative 302. So x1 is going to enter, and then we need to find the minimum for minimum ratio test. We use the minimum ratio test to find the minimum for that column. So we do the ratio is 7 divided by 1, that's 7. And then 10 divided by 2, that's 5. Yes.
Did you say that you're looking for the largest coefficient?
Largest negative coefficient for maximization. For minimization, we look for the largest positive coefficient. Yes. So R2 is leaving. X1 is going to replace R2 because it has the minimum value for the ratio. Yeah, that applies to maximization and minimization. Yes. So at this point, after we swap them, we have to make sure that this column for X1 represents the column that used to use R2. So we make the elementary row operations to make 0, 0, 1, that column belongs to X1. And after making those iterations, so we use the elementary row operations, arrows. We check again. Is there any negative coefficient? Yes. What's the largest negative coefficient? Negative 358. So that position variable will enter the solution, and we do the minimum ratio test one more time. So this one is going to be 2 divided by this 3.5. And then this one is negative, so we don't consider that one. So the only one that is available will be R1. So we're gonna swap X2 with R1. So again, we perform the elementary operations to make that column for X2 0, 1, 0, which is the format for R1. And now we have the final solution. If you check, there's no negative coefficient here in row 0. So we have found the optimal solution. And that is X1 equals 6 with 3 and 7, 3 over 7, and then X2 equals 4 over 7. And that's for maximization. For minimization, we're going to have the same formulation, but now okay, so this tableau, this first tableau is going to be identical. Here, if you look at the top, with the only difference that those coefficients for the artificial variable are negative now. Why is that? Let's formulate this problem. Okay, so now this is our objective function. Let me see where the space is here. Okay, I have some space here. So we are going to minimize z 2x1 plus 3x2 minus 5x3. And now here, since we're minimizing, want to penalize the objective function, I'm sorry, the artificial variables in the objective function. So the way you penalize them is by adding them to the objective function. Right? Because if you increase the artificial variables, let's say by 1, that's going to be a plus 100, and that's going to increase your objective function. And you don't want to increase the objective function, you want to decrease the objective function. So why are we penalizing them? Because we want the artificial variables to be 0 at the end of the solution of the problem. We want them to be 0 because they are not part of the problem. We are just using them to find an initial solution. So that's why I don't want R1 to be equal to 5 or equal to 10 or equal to something. I don't want that to happen because the artificial variable is not representing something in the problem. It's just there to find an initial solution to the problem. So I want to use them just to find an initial solution, and I want them to be 0 at the end of the problem. If they are 0, they're not making any, they're basically not deciding anything in our problem because they're equal to 0. So it's a modeling technique, okay? It's a modeling technique that we use just to find an initial solution in terms of x1, x2, and x3, or the slacks or the x's variables in this case. So we are adding the artificial variables in the objective function, and then we set up again this objective function in this way: 2x1 minus 3x2 plus 5x3 minus 100 R1 minus 100 R2 equals 0. So when we set up our coefficients, they're associated with that objective function: -2, -3, 5. So we have 0 for E1, minus 100 and minus 100 for the artificial variables. So the constraints, the coefficient for the constraints will be the same as previously. If you look at that first table, rows 1 and 2, the coefficients are the same. The only thing that changes was the objective function. So in the first 2 tables that I'm showing here after the initial tableau, what we are trying to do is to make sure that this is consistent. So this has to be equal to 0. So in the first table, we made that 0. In the second table, we made this one 0. So now the tableau is consistent. So since we are minimizing, we are looking for the largest positive coefficient. So we can now solve the problem. Largest positive coefficient is x1. So we're going to enter x1. We do the minimum ratio test. The minimum is 5. So that means that R2 is going to leave. So we're going to swap x1 with R2. And we're going to perform the minimum, the elementary row operations to make sure that x1 looks like this column. So after the first iteration, that's what we have here. This should be, this should be R1. Should be R1 here. So in this first iteration, we have completed the first iteration, and now we look for the largest positive coefficient. So that will be x2. X2 is going to enter. R1 is going to leave. So this should be x2 here. X2 is going to enter. We do the elementary row operations to make sure that this column now looks like this column. So arc x2 have entered. Do we have any positive coefficients here? Yes, we still have a positive coefficient. So x3 is going to enter. Based on the minimum ratio test, this guy is going to leave. So we make x3 look like x2. And at this point, we don't have any positive coefficient. So we have completed our problem. And the solution is x3 equals 4, x1 equals 3, and z equals minus 14.
Even though, as x2 as like an unspecified variable, we still want to replace it.
Yes, because that tells you you can find a better solution if you include x3 as part of the basics. And you can check that if you substitute these values, actually, you can look at the solution at that point. You see, this is a positive 14 with 4/7. And when you enter x3, that solution is decreased to minus 14. So x3 is giving you a better solution for the problem.
Is that like a way to check? Let's say is an example, like, if we enter x3, that the right hand side becomes like 73.
That will mean that the problem has an error.
Right.
Yeah, yeah, yes. Yes, so every time you enter a new variable, your objective function should decrease. If that's not the case, then there's something wrong with the computation. The way you verify this is by substituting these numbers into the objective function. So you have 2 times x1, so that will be 6. And then 5 times 4 is 20. So minus 20 plus 6 is negative 14, which is what we obtain here. Objective function here. Yeah, so what this is telling you is 2 times 3 plus 3 times 0 minus 5 times 4. And that's minus 14, which is the objective function. It's coming from here. Yes. For the previous problem? Yes, so the solution here is x1 equals 3/7, and then x2 equals 4/7. So your z is going to be 2 times 6, 3/7. So this is 7 times 42, 45/7, right? So this is 45/7 plus x2 is 3 times 4/7, and then plus, I'm sorry, minus, the minus times 5 times 0. So solution should be equal to 90/7 plus 21/25/7. My numbers are correct, and this will be 115/7. So how many times? Yes. Okay, so the next problem, this one was very simple. Basically, what I'm trying to check here is that you can formulate the right objective function for phase 1 when you apply the two-phase method. So it will depend on the constraints that we are considering as part of the problem. So for example, for a problem in which you're maximizing 5x1 plus 6x2, the objective function for phase one doesn't really matter, right? Because we are going to formulate phase one just based on the artificial variables that you are going to have as part of the constraints. So what we are looking at here, for example, for part A, we are looking at constraint. So for A, we have 1, 3, and 4. So we have inequality. See, for maximize 1, 3, and 4. So we have inequality. So this should be an artificial variable for, we need an artificial variable for the first one, but for this one, since we have a slack, and this one we have a slack, we don't need artificial variables. So the objective function for the first one will have only one artificial variable. Because the phase one for the two-phase methods is always minimized. Yes.
So for maximization, say R negative.
For maximization, well, what do you mean?
I mean, for example, I for A, I put this X size minus R.
No, but remember, this is for the two-phase method. So for phase one, the objective function is always the same. Is the minimization of the summation of the Ri's. So it's minimization of R, where R is the summation of the Ri's. So you're basically always minimizing the summation of the artificial variables for phase one. The two-phase method, you have two phases, right? Phase one, you're trying to find an initial solution and you are formulating the problem to achieve that objective. In phase one, you use the same constraints, but the objective function is always a minimization of the sum of the artificial variables. Right? So if we look at those three constraints only, we will need only an artificial variable for one of the constraints, which is the equality. So we only have to minimize the summation of the Ri's, since we only have one artificial variable, is the minimization of that, only that artificial variable. Let's look at the second one. So the second problem, I'm going to use a different color. We have 1. So we have for B, we have 1, we have 2. Okay, so 1, 2, 4, and 5. Okay, so for the first one, we need an artificial variable because it's inequality. For the second one, we need an artificial variable because this is a greater or equal to constraint. For this one, we don't need an artificial variable because we have a slack. And for this one, we have an artificial variable. So let me call it R5. So if we go back to this, for phase one, we have to do the minimization of R, which is the summation of all the R's. So in this case, that's R1 plus R2 plus R5, which is what we have here.
So, I wasn't consistent enough the thing. I like would rewrite. Like put on.
Oh, that's fine.
Okay.
As long as you have three, it doesn't matter what name you put in.
Okay.
The name has to be different. That's the main thing.
Because I created a like.
Yeah, yes. So if you did R1, R2, and R3, that's fine. As long as you have three artificial variables with three different names. Yes.
On how like on A, you said X minus D, 5x1.
Uh-huh.
How do we get this 5x1?
That's what this is trying to say is in this problem, this is your formulation. Maximize Z equals 5x1 plus 6x2. And then it's saying subject to these three constraints. So you are formulating this problem minus 2x1 plus 3x2 equals 3. The x1 plus 2x2 less than or equal to 5. And then 6x1 plus 7x2 less than or equal to 3. So for this first part, this is your formulation. And you have to do the same thing for each one of the problems. If you want to go through that level of detail, that's fine. But you don't need to, I mean, you don't really have to, because if you just look at the type of constraint that you have, you can know how many artificial variables you need, and then you can set up your constraint, your objective function based on that.
So for the first one, you already have the equal.
Yes, so it's an equality, so you need an artificial variable. Yeah.
Because the next one, you don't already have the slack.
Yes,
You don't.
we don't need it.
So in here, you just did S1, S2.
So for the first one, the objective function will be just R1. Yeah. Yeah. The minimization of R1.
What if I put for answer I put max Z equals 5x1 plus x2 plus f1.
That's not correct, because that's not the phase one objective function. Is always the minimization of the artificial variables. Yeah. So big M method, two-phase method, they're achieving the same thing, but there are two different strategies. With the big M method, you're subtracting or adding the artificial variables into the original objective function with the use of a large coefficient M. In the two-phase method, you have two phases. Phase one, you're looking for that initial solution by solving this problem. The minimization of the summation of the artificial variables constrained to the original constraints.
So for maximize the subject.
Yes, multiplied. Well, if it is a maximization, you are subtracting the artificial variables multiplied by this large coefficient n, right? Which is what we did here. You see?
And
If we minimize, we are adding the artificial variable. Two-phase method, phase one, always minimize the summation of the artificial variable. Okay?
So we have to state all of that, like, minimize.
Yes, all of them are gonna, phase one for the two-phase method is always the minimization of the sum of the artificial variable. This formula.
Even though like we have like on anything.
It doesn't matter. It's always a minimization, because what you're trying to do is to find an initial solution for your problem in which your artificial variables are going to be equal to 0. So that's why you always have to minimize this objective function because you are trying to make those artificial variables equal to 0.
So if we put SSN, it's not the well, like,
That's not correct. No, that's not the objective function for phase 1. That's not the objective function.
Okay, so I got it. What if we use the method?
If you use the M method, then the question is not asking that, but then that will be the original objective function. Mine is it maximization. You subtract the artificial variable that you need times the coefficient M.
It knows that. I knows it for phase 1.
This is phase 1. Yes. Yeah. Yeah. So this is problem 3. It's asking you to write phase 1 for the following problem and then solve to show that the problem has no feasible solution. Okay, so we have the formulation here at the top. We add the artificial variable for the first constraint. We don't need an artificial variable for the second constraint. So subtract the excess variable, add the artificial variable. You see the objective function is the minimization of just that artificial variable R. With the original constraints, make them equality. So you subtract U1, you add S2. So this is your problem that you're going to solve using the phase 1. So you set up your initial tableau, right? So you are minimizing the summation of the artificial variables. So once you set up your initial tableau, you need to make sure that this is consistent, right? So we are going to make this equal to 0. So we perform that iteration, remember, to make the problem consistent. So this should be equal to 0. So we perform the elementary row operation before we attempt to solve this problem. So after making that equal to 0, you see how the column will look like. And then at this point, we can solve the problem. So we are minimizing, so we are looking for the largest positive coefficient, which is 3. So X1 is going to enter. We perform the minimum ratio test. The minimum is for S2. So S2 is going to leave. So this column now, since this is going to enter and S2 is going to leave, this column should be 0, 0, 1. So we are going to perform the elementary row operations to make this equal to 0, 0, 1. So after performing that iteration, this is the resulting tableau. We still have a positive coefficient. So that means that X2 is going to enter. We perform the minimum ratio test. And the ratio is telling us that X1 should leave. Right? So X2 is going to enter. X1 is going to leave. So that means that X2 has to be made 0, 0, 1. Because it's replacing X1. So after performing that iteration, we have 0, 0, 1. At this point, we check again if we have any positive coefficient in row 0. The answer is no. So we have found this is our last iteration. So this will be the optimal solution for the problem. So the question is asking, show that the problem has no feasible solution, which means show me that this problem is infeasible, right? That it cannot be solved. So if you remember in my explanation, I always stated that at the end of the first phase, we need to check that we don't have any artificial variables that are part of the basic. And if we have a basic variable, an artificial variable that is basic, we need to make sure that that artificial variable is equal to 0. If that's not the case, then the problem has no solution, cannot be solved. So that's what we observe in this problem. You see, we have an artificial variable that's still basic and has a value that is 2, equal to 2. It's not 0. So we want the artificial variables to not be part of the basic, but if they're part of the basic, they have to be equal to 0 in order for the problem to be feasible. So that's not met in this problem. So that's why we end up concluding that this problem has no solution, because we have an artificial variable that is part of the basic and doesn't have a value that is equal to 0. If you look at the problem, at the original problem, I mean, this is just showing you what's true, right? If you look at this problem and you look at these constraints, there's no way that you satisfy those two constraints. There's no combination of numbers that will meet those constraints. You can try to find it, but it's not going to happen. So that's why the tableau is showing you, if you use the artificial variables, there's no way that you will find an initial solution for this problem. In which the artificial variables are going to be equal to 0, because there's no feasible solution. The problem is infeasible. There's no way that you can solve this problem. So the tableau is telling you, again, this is infeasible. No solution for this problem. The way you identify that, again, you solve the first phase. R1 should be equal to 0. How do you know it's going to be equal to 0? Well, if it is not part of the basics, all non-basic variables are equal to 0. But this one is still part of the basics. So we check the solution. Oh, this guy is equal to 2. No solution. Artificial variables must be equal to 0. The problem is infeasible. Okay, do you try to solve the problem? Find any combinations that meet these. If you make x1 equal to 2, then 3 times 2 is going to be greater or equal to 6. But 2 times 2 is not going to be less than or equal to 2. Right? If you make x2 equals 3, 2 times x2 is going to be 6. So it will meet the first constraint. But 3 is not going to be less than 2. So yeah, there's no way. There's no combination of x1 and x2 that will meet these two constraints. The problem is infeasible. And the tableau is showing you that. Okay. And in practice, you might find problems like this. I mean, this is a simple example, but if you have a large problem, you have a lot of constraints. Maybe one of those constraints is forcing you not to meet other constraints. Maybe the budget that you have available is not enough to meet some of the constraints for your problem. So when you try to solve the problem, you'll see that this problem is infeasible, no solution. It's because some of those constraints are forcing you to not meet other constraints in the problem. So in those cases, you're going to have to go and check whether you can formulate the problem differently, or if you can add more resources to your project. So you can modify the values, let's say add more resources or more money to the project so you can meet those constraints. Or maybe do not consider certain pieces of the problem. So you basically redesign the problem or the project so you can find a feasible solution that meets the constraints. And that's the last problem for the assignment. Okay, so again, I want to go back to this, the exam, second exam, Wednesday, October 27. There's going to be 2 parts. Exam part 1, 3 problems to be solved by hand. The exam is going to be available in Canvas, so it's online. If you have computer in your home and you have access to the internet and you have the software that is needed to solve the problems, you don't have to come to class to solve the exam. However, if you don't have access to a computer or to internet, or you don't have access to the software to solve part 2, you have to come to class. I will provide you with a laptop to work on the exam. Exam part 2. So for the first part, you have 90 minutes to work on the exam. It's from 9:30 to 11 a.m. So you have to upload your answers to those 3 problems within the scheduled time for the class. Exam part 2, you will have 24 hours. In the second exam, in the second part of the second exam, you have 2 problems to be solved using the computer, using Excel, and the second problem will ask you to use Ample. The exam also will be available online in Canvas. It will be available from 9:30 a.m. on Wednesday, October 27th, and it will be due on Thursday, October 28th at 9:30. So you have 24 hours to work on the second part of the exam. Hope everything is clear. If you have questions, I have office hours tomorrow from 8:30 to 10:30 a.m. I'll be available. And if you have questions, you can send me also an email. If you cannot meet during that time, I can try to schedule a separate appointment. You just have to communicate with me via email. Any questions?
Can I upload this file?
Yes, this will be uploaded. I have a meeting at 11, so after my meeting, I will upload everything. But the notes, there's some notes here. Yeah. Yes. So I will upload, let's say by noon, should be available. Also, the video should be available by noon. Okay, I'll see you. Well, if you have to come, I'll see you on Wednesday. If not, then I'll see you next week.